Well, greetings, mathletes, and welcome back. In the last lecture, we talked about trigonometry and how to view all the different trig functions: sine, cosine, tangent, and their reciprocals. Um, Today, we're going to be revisiting that, but we're going to be putting it into a slightly different context. Where what we're actually going to be doing is putting it on a coordinate system, so we can actually mess around with it. Um, in any case, let's go ahead and get started here. So I want to start off with a little bit of review from what we did last time. Um, so first off, I just want to go through the definitions again. Right? If I have a right triangle, ooh, that's a pretty good right triangle, and an angle theta, right? This side would be the one that's opposite to theta. This one is adjacent, and this is our hypotenuse, right? And our different functions here, if I have sine theta, this is going to be the opposite over the hypotenuse. Cosine theta is the adjacent over the hypotenuse. And tangent is the opposite over the adjacent. Right? So these are all ratios of triangle sides. That's what we want to remember first of all, and then we can remember these three with our SOHCAHTOA acronym. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Right? So that's how you remember those. Now, we also had the reciprocal identities for these things. So cosecant is equal to one. Oh, boy, I did that wrong. Let's try that one more time. Cosecant theta, there we go, is equal to 1 over sine theta. Right? So whatever I find for sine, if I flip it, if I take its reciprocal, I have the cosecant. So sine is opposite over hypotenuse, which means that cosecant would be the reciprocal of that, hypotenuse over opposite, right? Okay, and then cosine, I said cosine and I started to write sine. Okay, let's try that again. Cosine's reciprocal is secant. Secant theta is 1 over cosine theta. And lastly, tangent. Tangent's reciprocal is cotangent. And what that means is that cotangent is adjacent over opposite, right? So you can just take those ratios and flip them all over for the reciprocal ratios. And again, the way I pair these up, whether this helps you or not, this is how I remember it. Sine and cosine's reciprocals, if you pair them up, sine goes with cosecant and cosine goes with secant. Notice it sine starts with S, cosecant starts with C. So you get one that starts with S, one that starts with C in each case. So sine and cosecant, and then cosine and secant. And that's not a mathematical way to remember it by any means, but it's a definition. So it's just a matter of remembering what it actually is. And then tangent and cotangent pair up, right? Those tend to be reciprocals of each other. Okay, so those were the basics that we looked at this last time. Now, let's go ahead and erase that. So let's do this. Okay, so what we're going to do is we're going to redefine trig on something called the unit circle. So let me go ahead and start by drawing a circle. And let's start again. Let's try this one more time here. Okay, so let's try a unit circle. There we go. I'm getting better at my circles. I'm starting to be very pleased with that. Okay, so here's my circle. I know it feels weird defining triangle functions with a circle, but it's a unit circle, which means that its radius is 1, right? So the radius is 1. And we're going to put this on a coordinate system. We're going to center this circle at the origin. Okay, so there's some things we can pick out here. Just knowing it's a unit circle and has a radius of 1, we can start marking things on here. Like we know what that point is because the radius is 1. That means this length right here is 1, which means my x-coordinate here is 1. And it's on the x-axis, means my y-coordinate is 0. Also up here, I can do the same thing. I can actually just look at it. Since I know the radius is 1, this distance here is also 1, which means that this has the points, the point 0, 1 on it, right? And likewise, this could be -1, 0, and this could be 0, -1. Right? So you can actually piece those things out just to start with. These are just things that you can figure out. Now, let's take a look at this angle here. So again, our angle theta now is in standard position. You notice that that's how I've drawn it, right? It goes on forever, but what we're interested in is that coordinate right there. So knowing that this is an x and a y coordinate, let's take a look at this. So that means that we can drop down a vertical here, and notice I have a little right triangle, right? And I can do this no matter where I put this point. If I put this point over here, I can still draw a little right triangle in here. Ooh, that's not a great right triangle, but we'll go ahead and just go with it, right? So, what was I saying? Yeah, so anyways, we can still look at this angle here in standard position. So I'm going to call this angle theta. Just as a warning, that angle does get called a lot of different things, not just theta. It's typically a Greek letter, though. Okay, so we have our angle theta here, and let's just look at what happens as we define this stuff. So this side of the triangle is actually the height of the triangle, right? But it's also your y-coordinate, which is kind of fun. And then this side right here is the x-coordinate. And when I say x and y coordinates, I'm talking about the same ones that are right here, right? It's those x and y coordinates. So let's take a look at something here. Suppose I wanted to take a look at sine theta, right? Sine is opposite over hypotenuse. And so let's see, the opposite side is y and the hypotenuse is 1. So that means that this is y over 1, but anything over 1 is itself. So I get that the y-coordinate, just from this right here, that tells me that the y-coordinate is sine theta, right? And so that means that anywhere I put that point, if I can find the y-coordinate, I know what sine of that angle is, even if I don't know what the angle is. Okay, now let's look at cosine. Cosine theta would be adjacent over hypotenuse, which is x over 1, which is just x, which means that my x-coordinate is cosine theta, right? So if we redraw this unit circle here, I'm going to attempt to redraw it. Oh, let's try that again. I don't know if I'm just too stubborn to use the circle drawing tool or what, but anyways, if I look at this now, what that means, let me move this, let's sit up in the corner here, is if I draw any angle, no matter what theta is here, as long as this is a unit circle, that length is 1, then these coordinates here are cosine theta and sine theta. Ooh, that's terrible. Let me try that again. Right, these coordinates are cosine theta, sine theta. Right, so x is cosine, Y is sine. This is why you don't often see, especially if we're going to be doing anything with coordinates, you very seldom see things like sine of x or sine of y. You will see those things later, but it causes a little bit of confusion since the x coordinate is the cosine and the y coordinate is the sine when you're dealing with the unit circle itself. Um, Interestingly enough, which is also kind of fun, um, so let's see, what do I want to pick out of here? Um, I'm just gonna get rid of all of it. Hold on a second. Let's do this. I'm gonna get this guy out of here. All right. Now the equation of a circle, um, particularly a unit circle, is, oh geez, let's try it again. There. Okay. The equation of a circle, let's try this one more time, particularly a unit circle, is x squared plus y squared is equal to the radius squared. Well, the radius in this case is 1. So I have x squared plus y squared equals 1. Well, if you remember, cosine theta is x squared. So that means I have cosine theta squared. Notice I use parentheses. Over here we have y. Well, y was sine theta. So that means that cosine squared plus sine squared is equal to 1. And actually, just so we understand the notation, this is almost never written this way because having the parentheses and the square gets awkward really, really fast. So what we write instead of this, and just know that when you see this, this is what it means. If I want to square cosine, I write it this way: cosine squared theta. And what that means is to take cosine theta, and then whatever number you get, you square that number afterwards. So writing it this way means this, just so we're clear on that. And then sine squared would be written this way, equals 1. And this is called the Pythagorean identity. It's always true. It doesn't matter what the angle is. If I look at, I don't know, let's say theta is equal to 6 pi over 15. Let's make it over 17 so it's obnoxious, right? Cosine squared of 6 pi over 17 plus sine squared of 6 pi over 17 is equal to 1. No matter what. You don't have to know what cosine of that or sine of that is. In fact, that would be quite difficult to do by hand. That's something that you would want to plug into a calculator. But it doesn't matter what the angle is. If I pick a negative angle, a positive angle, an angle that's bigger than 360 degrees, an angle that's smaller than 360 degrees, it doesn't matter what angle I pick. This is always, 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 always going to be true. And so you'll see stuff like that in your homework where it's like cosine squared of 1.7 plus sine squared of 1.7. And you might even be thinking, is this degrees or radians? It doesn't matter. Because if they're both the same number, as long as you're putting the same number into both sine and cosine, then the sum of their squares is always going to be 1, no matter what. And so that's kind of a nice little trick because it really does simplify things a lot in the long run. When you're multiplying things out, very often a sine squared plus a cosine squared shows up in there, and you can simplify it down to the number 1 and not have to worry about a bunch of other stuff. So it is quite convenient. And we will be using it a lot. In fact, most of the stuff we used that we learned today will be required knowledge for the rest of the semester. The unit circle definition is very, very, very important. Okay, so let's go ahead and move on to the next thing here. Oops. That is not what I meant to do. There we go. Okay. Okay, so for this next part, you're going to need to get the worksheet that I that I posted with the assignment, and it should look like this, right? It's the fill in the unit circle. We're going to actually draw this on um, a separate screen here and play with it so we can draw it on here. Let's see. It's good. Okay, so I went ahead and used the drawing app this time. Let's go ahead and blow this thing up. Well, not that much. Let's do about right there. Scoot this over and scoot this up. Okay, so here's how this ends up playing out. You know, when you're dealing with these things, you have 4 quadrants, right? Remember that this is, oh, let's try this again. This is your x-axis, and your y-axis is this axis over here. Now, we have special triangles we can play with, right? We have that 30, 60, 90 triangle. Ooh, boy, the writing on this, the pixels are getting bad. I wonder if I can do this. Oh, wrong way. Maybe I could just do it there. Okay, let's try this one more time. A little bit better, right? So we have our 30, 60, 90. And then the other one we had was our 45, 45, 90. Okay, so those are the angles that we're going to be paying attention to. So the first one, in fact, let me go ahead and switch colors here. Maybe I can do it this way. There we go. This would be 0 degrees. And it's also 0 radians. That's actually what those things are there for. You have one that has the degree mark, and so you're supposed to put in degrees, and the other one has the radian, doesn't have a mark at all, and that's the one for radians. And then you have a coordinate, right? And I know the coordinate here is 0, 0. Or, excuse me, 0, 0, 1, 0. Try that again. Okay, now we want to break this up into our other angles. So we have 30 degrees, 45 degrees, and 60 degrees. Right? And that's this angle, and this angle. Right? So those are those 3 angles. And then we have 90 degrees, right? 90 degrees up here. Now, we've gone through the conversion before, and it wouldn't hurt you to do the conversions again just to make sure you have them. So for 30 degrees, we know this is the same as pi over 6. 45 degrees is pi over 4, and 60 degrees is pi over 3. Right? So those are the angles that you're talking about here. And then up here at 90, we're at pi over 2, because remember, pi is the same as 180. So that's a full reversal of direction if you go 180 degrees. So, and that's pi, so half of that would be 90, and so that's pi over 2. It's half pi, basically. Okay, so we have those things. Now, one of the things that we're going to have to get used to is thinking in terms of radians, because right now we're used to thinking in terms of degrees. And so these end up being our references. This first quadrant ends up being the most important out of all of them, because you can map every other quadrant's angles out of the first quadrant. So let's go ahead and take a look here. If we remember our side proportions, this should be 1, 2, root 3, and so that will help me find my 30 and my 60. And then over here, remember we have 1, 1, root 2. And so we just want to start building these things, sine and cosine of this. So let's start with 30 degrees. Cosine is our x-coordinate, so that's going to come first. So for 30 degrees, cosine is root 3 over 2. Okay, sine, right, would be, since we're talking about this angle, would be the opposite over the hypotenuse. So sine here is 1/2. Now we move up here to 45 degrees. So I'll turn over to my 45, 45, 90. And what I get when I take the cosine of 45 degrees, I get 1 over root 2. And if you remember, 1 over root 2 needs to be rationalized by multiplying by root 2. And that gives us root 2 over 2. And so that means that this is going to be root 2 over 2. And if I want to find the cosine, it's going to be the adjacent over the hypotenuse. But again, that's 1 over root 2 again. So we get the same thing. Boy, I'm running out of room real fast here. So this is also root 2 over 2. And then lastly, here we have 60 degrees. Well, 60 degrees is here. And remember, this is root 3 on this side. So if I'm looking at 60 degrees and I want to take its cosine, right, that would be the adjacent over the hypotenuse. So the cosine's 1/2, and the sine would be root 3 over 2. Right? And so, there we go. What do you call it? So there's some things to notice here. One, you notice that this and this are just reversals of each other. The x and y coordinates reverse, which is actually kind of nice. And there's definitely a strong relationship between. Hang on a second. There we go. Let's do this. There's definitely a strong relationship between the what do you call them? Between the sine and the cosine, and it's because the ratio is off of the same triangle, right? So sine of 60 is cosine of 30. Sine of 30 is cosine of 60, right? They actually have that interesting little relationship between them. Now, what's also nice is these angles that line up on your axes are called quadrantal angles. And the quadrantal angles are the ones that don't require a triangle. In fact, you couldn't really draw one because one of the side lengths is 0, right? So quadrantal angles, you just have to look at them, and you can tell just by looking at this that the coordinates are 0, 1, right? Because that's where it's located. Now, now that this thing's turned into quite a mess here. Let's see if we can do this. Let me try switching over to this thing. No, we'll leave it here. All right. So now here's the other thing that will help you. The fact that these are coordinates, right? So that means over here, all the x values are positive. On this side, all the x values are negative, right? So that means if you are on the left-hand side of the y-axis, all of your values of cosine will be negative, right? You can actually figure that out ahead of time. And what's more is as you fill in these angles, let's see here, what would this angle be? This angle has to be straight across from this one. This angle is going to be straight across from this one because they have the same angles. So as I go through this, right, this is still 30, this is still 45, but you notice I'm measuring them from a different place. I'm measuring the other side. But because of the fact that these are the same angles, the only thing that we have to really worry about is switching the signs. So, for example, here, if I want to transfer these two things over, okay, so I know this is 60 degrees less than 180. And so this would actually be, if I'm counting from this side over here, let's switch that color. If I'm counting the angle from this side, it would be 120 degrees because they have to add up to 180. Right? Now, if I want sine and cosine of 120 degrees, Let's see here. So x is cosine. So 120 degrees behaves like 60 degrees. You can see because this is the other side of it. So let's look at 60 degrees. Cosine of 60 degrees is going to be 1/2. But because it's an x coordinate and it's on the left side, all the x coordinates are negative here. So that's negative 1/2. Then over here on the other side, let's see here. So we're still going to use 60 degrees. That's going to be our reference to find the sine of 120 degrees. And notice here, the sine of 120 degrees is the height, right? It's how far above the x-axis it is. That's actually the measurement it's telling you. So the sine of 120 degrees is going to be the same as the sine of 60 degrees, which would be √3/2. Right? And so you're piecing these together. The same thing's going to happen over here. Boy, my camera's moving around on me. Let's scoot that just a little bit. Right? This one lines up with 45. So that means it's 45 degrees less than 180, which makes it 135 degrees. Right? And you would also need to switch that to radians and get, so you can get used to the radians as well. But the x and y coordinates are going to match these. It's still √2/2, comma √2/2 for the coordinates, but scoot this over a little bit. But this one's negative. There we go. Right? Because the x coordinates are all negative. Down here, if I take this down to the third quadrant, both cosine and sine are negative here. Over here in the fourth quadrant, cosine is positive, but sine is negative because cosine's an x value. All the x values are positive. Y values are negative, right? And so cosine is positive and sine is negative. And so you want to just go ahead and walk through the rest of this and try to piece that together. Piece together the whole circle. That's going to be a task for you guys. If you're having trouble with it, again, come and see me. There are definitely ways to do this. And not only that, I think I'm going to post a filled in copy of this thing too, so you can check yourself and make sure you're understanding how to put it together correctly. The main thing you want is to understand how it's put together so you can come up with this stuff on your own as you go through. But I want to point out something else here, which is kind of interesting about this, is you'll notice that what this is really doing when you look at this stuff, let me put it over here, I guess, more than anything else, you're taking an angle, right, whatever that angle is, and you're finding two distances. You're finding this distance, and you are finding this distance. How far it is from the x-axis, how far it is from the y-axis. And that's going to depend on how far it's rotated. So this is a way of relating rotational distances with linear distances, with distances in a straight line. Okay, so let's go ahead and take a look at the next piece here. Let's do that, delete that, and okay, now the unit circle will also give us some other interesting properties. Let's see here. So let's go ahead and try this again here. Okay, one more try. Yeah, not too bad. Want it to be big enough too. Okay, so here's one of those interesting things. This is related to what are called the even and odd properties. Properties, or well, it's a property. Now this isn't always true. Excuse me. This is always true, but it's not only true for trig functions. Other functions are called odd and even, and basically what makes a function odd or even. A function is even if when I plug in the negative value of x, it's the same as plugging in the positive value for x, right? So what that means is that if I plug in something over here, it's the same. I get the same value as if I plug in something equally spaced on the other side, right? That's basically what that means. Here, this would be positive x, this would be negative x, and what it's saying is that the y values of both of these things are the same, so they should be at the same height, whatever that means for that particular function. If you have an odd property, a function is odd if taking f of negative x is the same as taking f of x and making it negative. Now, just a quick example here. Probably the standard even function is x squared. You can test to see if a function is even or odd. If f of x is equal to x squared, this is an even function, and you can show it by showing that f of negative x is equal to negative x squared. And anytime I square a negative, I get the positive. So this is the same as x squared. And x squared is the same as the function value. F of x is also equal to x squared. And since negative x gives me the same value as positive x, what that means is that's an even function. What would make it an odd function, if I had changed the exponent to a 3, the cube of negative x is negative x, so it stays negative. And what that would mean is that plugging in negative x gives me a negative function value, right? Gives me the opposite of the positive function value. So yeah, you have those little issues in there. Now, I did a really quick explanation of this, but it's mostly just so we can look at sine and cosine in terms of this, because one of them is an odd function and one of them is an even function. So let's take a look here. Let's just pick an angle. That I had the eraser on. Let's try this again. So let's pick an angle here, right? So here's an angle, here's a point. And we know that the x and y's are sine and cosine, and they are functions of this angle theta. So let's start by just looking at this. If I look at sine of theta, right, and we want to know if it's an odd or an even function, what we do is we check and look at sine of negative theta and see what happens to it. If we get sine theta as our final answer, then it's an even function. If we get the negative of sine theta, then it's an odd function. So let's look at what negative theta means. That means that we're going downwards this direction, and this would be negative theta. So that projects us down this way, right, to the bottom. And this value, this height right here, is going to be the same as this height here. But this one is negative. And remember, the y value is your sine function, right? So this side is sine. So this is sine theta. This is sine of negative theta, right? So the sine is actually a length here. If this is sine of negative theta, well, let's look at it. It's actually the same coordinate as you get with positive theta, but it turns out negative. And so that we can see just from the picture that sine of negative theta is the same as negative sine theta. And so because this is the same thing as negative sine theta, that means this is odd, right? Okay, so that means that sine is an odd function. So I kind of don't want to erase too much here, but if it's odd, that means if I take any value, like if you need to find sine of negative pi over 3, that would be the negative of sine of pi over 3. And so if you can find sine of pi over 3, all you got to do is slap a negative on it. right? And so it's a handy little thing to have. Now, I want to take a look at um, cosine, right? And remember, cosine is this side of the unit circle, right? It's that x coordinate. So let's see what happens to cosine of negative theta, right? Let's see what happens to that. So if I look at cosine of negative theta, that puts me down here, right? And let's see here. Negative theta, the cosine would be the adjacent over the hypotenuse, which is the exact same value, right? Because this was our x value, and that's a 1. Cosine of negative theta is still x over 1, which is x, and x is equal to cosine theta, right? So we got the positive value back. And so what that means is that cosine is an even function. So if I take cosine of negative pi over 2, that's the same thing as cosine of pi over 2, right? I can just take the negative off of things that are inside of cosine. That is of huge use also, right? So you're going to get the same thing either way. So that's kind of a nice little piece of computational convenience there. You can just kind of, with cosine, if the angle's negative, you can just turn it positive and you get the same answer. Okay, so let's go ahead and look at the last piece here. And the last piece has to do with periodicity. Okay, so this idea of periodicity, in fact, let me write this down here. Yeah. Periodicity, or periodic functions. They're functions that repeat themselves, basically. And sine and cosine, actually in tangent, cotangent, secant, and cosecant, all of them are periodic functions. The period is how long it takes to repeat itself. So, for example, with sine, right? I'm just going to do this in degrees because it'll make things a little bit easier. I know if I start with 30 degrees, if I continue to increase and I go a full circle, right, and add 360 degrees, what I'm really doing is finding a coterminal angle, right? And so this idea of periodicity links in very, very strongly with that idea of a coterminal angle. Most of the time, what you're looking for is the coterminal angle that goes into the first revolution. And what's really nice about periodic functions is that because of the fact that they repeat themselves, all you have to worry about is everything that happens in the first period. Because after you figure that out, the revolutions are all the same, right? The more you redo it, the more you get the same answers. And so I want to take a look at this. Here's a little display that I put up here. So you'll notice here, I went ahead and I marked the sine and the cosine of this angle here. Now we actually have 2 points sitting on top of each other. If I'm going to add 360 degrees to this, really what it's doing, and I just want to pause it right there for a second. This second angle here has its sine and cosine marked over here, right? And so these are the actual decimal approximations of their sine and cosine values of this point right here. So as I animate this, you can see these values changing, and they'll go all the way around the entire circle. And as they come back to where they started, you'll notice their values will start to match again. Let's see if I can pause this in the right place. Oop, almost. Very, very close. Let me just do it by hand here. Right? Once I do a full revolution and come back to the same place, you can see that all these values are the same again. Right? And so every time it goes around once, you're back where you started from. So all you really have to worry about is what happens in the first period. And then from then on, you know it's coterminal with anything else. It saves you a lot of computation in the long run. Now, if we're going to write this formally, actually, let's do that. A function is periodic with a period of p, and so I'm just going to use p for period, if f of some value a is the same if I add p to it. Right? So a plus p, the function value from a plus p is the same as the function value from a. What this means is that whatever that value was, it's going to come back up. So you can pick a value for a. As long as you're adding the period, you're going to get the function value for a no matter what you do. Right? Now, it's a matter of figuring out the period here. With sine and cosine, both of them are periodic functions. They both have a period of 2 pi. Right, which is the same as 360 degrees, right, if you're dealing with degrees. One thing you will notice is that the farther we go in here, probably the less we're going to be dealing with degrees. When you get into calculus and stuff, almost everything is radians, so just be aware of that. I keep throwing the degrees down for reference. They are used a lot in engineering just because it's a finer measurement than radians, so do be aware of that. Nonetheless, this is basically just a shortcut so that you don't have to reinvent the wheel, so to speak, the trig wheel, actually. Okay. Now, so let's go ahead and recap the things that we talked about today, just to make sure we got everything down. Okay, so first off, we talked about the definitions, and I reminded you that you can, with sine, cosine, and tangent, you have those definitions. Oh, I did it again. Yeah, here we go. Sine theta, cosine theta, and tangent theta we had, right? And we had that SOHCAHTOA definition for that. But then we found out that cosecant, in fact, we talked about this last time, but I started out with this. Cosecant is 1 over sine theta. Secant is 1 over cosecant theta. Try that again. Cosecant theta. And then cotangent is 1 over tangent. Okay, then, right, so this is actually, as we go into the next chapter, these guys will be very important. These are the reciprocal identities. Another thing to point out, and I didn't point this out earlier, I pointed it out in the last lecture, but I'm going to add it in here anyways, is that tangent theta is equal to sine theta over cosine theta, and cotangent theta is equal to cosine theta over sine theta, right? Because it's the reciprocal of tangent. Okay, so we got that. Then we talked about the Pythagorean identity, right? The Pythagorean identity. In fact, let me give these names here. So these are the reciprocal. Well, my handwriting is awful. Identities. These are the quotient identities. Okay, these are called the Pythagorean identities because they're based on the Pythagorean theorem. A squared plus b squared equals c squared. Right, and so cosine squared theta plus sine squared theta let's try that again. There we go. Sine squared theta is equal to 1. And then if you divide everyone by cosine, you get 1 plus tangent squared theta is equal to secant squared theta, right? So that's another Pythagorean identity. And if you take this one and now instead of dividing by cosine, you divide by sine, you end up with cotangent squared theta plus 1, or excuse me, divide by sine squared, is equal to cosecant squared. Right? So these guys are pretty closely tied together. Cosine goes with sine, tangent goes with secant, and cotangent goes with cosecant. So it's kind of interesting looking at how these things map together. Now, you do need to memorize these. These guys will come up a lot. And notice, too, that you can manipulate these. So, for example, I could, if I subtract sine squared from both sides, I can say that cosine squared is equal to 1 minus sine squared. Oh, cosine squared theta. I keep forgetting the argument. Right? I could also take like tangent and secant. Secant squared minus secant squared theta minus tangent squared theta is equal to 1. Right? And that's just manipulating things that are already there. So you do often have to have alternate forms of these identities as you go through. So just be aware of that. You're allowed to manipulate the equations how you want to. So, but yeah, these are the main things. These are your main identities. And honestly, as we go farther into this, one of the tricks that's going to be really, really helpful, you notice everything can be written in terms of sine and cosine. Cosecant, sine and cosine or sine and cosine, but cosecant can be turned into a sine function. Secant can be, oh, I wrote that wrong. That should be cosine. I'm getting old. Okay. Let's try that one more time. Okay, where was I? There we go. That should be cosine. Okay, yeah, I should have spent more time reading the Bible because it says, secant you shall find, and I didn't find it. So, anyways, so my point was, you can rewrite cosecant in terms of sine. You can rewrite secant in terms of cosine. You can rewrite tangent in terms of sine and cosine. And you can rewrite cotangent in terms of sine and cosine. So everything can be done in terms of sine and cosine. And that's going to be an advantage later on. Because if you can get everything boiled down to sines and cosines, those are a lot easier to manipulate. You only have 2 things to play with. Instead of like 5 different functions, you can break it down to 2. So it really does help quite a bit. Okay. So that's the end of this lecture. And so until next time, you guys, keep your pencils and your wits sharp. And I'll see you later.